finish, I showed you that, okay, this we won't reach immediately. I showed you that now we can push bosonization to a quantitative art. I already showed you this ladder systems. I just, okay, this, let me skip that. It's not important. I want, of course, to show you, was there a low technology pointer or high technology pointer? Yes, here's the laser from hell. That it works also for fermions, not just for bosons. Essentially, you get power laws all over the place, just like you had for bosons. Essentially, for example, you get power laws which are characteristics of Luttinger liquids in the conductivity, in the optical conductivity of these organic metals that I was mentioning before. And this is something which is testable experimentally. Here are experiments which were done in the group of George Brunner at UCLA, Martin Dressel, and Leo De Giorgi. And you see this weird absorption spectrum as a function of frequency, and when you plot it on a proper logarithmic scale, you find a nice power law, which is telling you that these materials are Luttinger liquid. And to the best of my knowledge, this was really the first observation of Luttinger liquid in condensed matter. If you do the nanotubes, if you take the nanotubes, you have similar type of behavior, where by measuring the conductance as a function of temperature, you do see power law-like behavior. And again, this has been interpreted, there is some little debate on it, but this has been interpreted as the signature of Luttinger liquid behavior. Okay, so far so good. We have dealt with a clean system, and now we have to go to the other end of the spectrum and try to talk about dirty bosons. Okay, so I'll try to put the disorder back into the bosonic system, and I've given you already some level of experimental motivations. But first, what I would like to give you before we start with the problem at hand is a sort of general introduction to disordered systems. And you already got some view of this in the lecture by Anton before. So you know that disorder is a little bit more complicated, because of course you have to deal with this random impurity. So the general idea is that we have a problem which I will call H0. H0 is not free particles, and that will be what will be the essence of my lecture. After, I want to consider many-body localization. I want to consider many-body effects together with the disorder. Okay, but here H0 means, or if you prefer, let me call it H pure here, and then you typically add to this something which is some integral of a space of a certain potential, which can couple to the density, can couple to other part of the system, like the kinetic energy and so on. But in what I will tell you in these lectures, I will couple this object to the density. And now V of x is a random variable. And of course, then what you want to compute are the physical properties of such systems. Now the problem, so for example, if I just say I get impurities put at random positions Ri, I can consider that V of x would be something like sum over I of delta of R minus Ri times the amplitude of each impurity potential, V0. This is what people call typically a Poissonian disorder. So you throw a bunch of impurities on the table, they get positions which are completely random. So let's say Ri are random, and essentially, doesn't want to scroll up. Yes. Ri at random, And so I have here a disorder which is characterized by two numbers. One is V0, the strength of disorder. And the second one is the average, let's say, density. So I don't know how to call it, N, the average density of impurities. Impurities. Okay, so, and again, that's what people call Poissonian. Now, of course, once you have a problem like this, you're typically, it's very complicated. For why? Because we are so much used when we deal with a pure system to use translational invariance, which allows us to go from real space to momentum space, and so on. And all this is completely lost as soon as you add impurities. What is worse is that you do not want to compute an observable. So typically, let's say, as you saw before, you want to compute, let's say, some correlator, so some average of some operator, which I don't care about for the moment, the current or the density or whatnot. So this is the quantum average. But this quantum average is made with this Hamiltonian H pure plus whatever V rho. So this is a random variable. So every one of these objects will depend explicitly on the realization of the disorder you have. And you can be very unlucky. Imagine I throw my impurities and I just put them very regularly in the system. Okay, you have to cheat to do that, but okay, you can do that. And then what I will compute as an average is not at all characteristics of the disordered system, but what I will get is the characteristics of a system with a periodic potential. So what you really want to do at the end is the average of a disorder, and this average, you hope, will give you the physical properties you want to look at. So what we really want to look at is something I will denote like this, which is the average of a disorder. So this is the integral over all the realization of the disorder V times the probability to find a certain realization V of the object here, which is the quantum average done with H pure plus, let me write it that way, 0. Okay? And doing this second average can be trivial or can be complicated, but you see that we have something which sounds a little bit crazy to do. We have to solve something for any realization of the random potential, even the least probable. Then we have to average. I assume here that the integral of P of V is 1, and it's a probability, so otherwise I will have to divide, if you want, by the integral over dV of P of V. And then we have to get this double average, the quantum average. When I say quantum, I mean thermal and quantum. I put everything in the same, I can do quantum physics at finite temperature. And this is the disordered average. And that's what makes the disordered problem quite complicated, is that you have to do this double average, and this is what people also call, I should have introduced the name, but I'm sure you heard it about. This is what people call quench disorder, which means the disorder doesn't move. So the disorder realization is totally ignoring what your quantum system likes or doesn't like. You throw the impurity in the system, whether the system likes the configuration of impurity or not, the disorder doesn't change, it doesn't move, it's fixed once and for all. There is another type of disorder which I will not discuss in this lecture, which people call annealed disorder, where the impurities can move a little bit, and they try to optimize their position with what makes the system happy. In a way, it's not very different than electron coupled to phonons. You can view the distortion of the lattice due to phonons as a random potential, except this random potential fluctuates, move with time, and try to optimize together with the electrons. But here I want to freeze the phonons, if you want. I want them not to move, and that's what people call quenched disorder. So the point is that once you do the average of a disorder, you recover a translationally invariant system. So it sounds a little bit crazy to do it in this way, and so people have tried to find ways to do the averages or to deal with the averages from the start, to get rid of the complication of losing translational invariance, of having to deal with specific realization of the impurity potential. Okay. So I will briefly mention the methods that people try to use to do that. Before I do that, let me sort of simplify my life, because Poissonian disorder is pretty complicated. Okay? So I would like to move to a simpler class of random potential, and for that I can sort of simplify my life for the case where the disorder is weak. And so the characteristic property of the system varies slowly at the scale where the impurity are located. So in a way, I can view my system as weakly distorted, but I have plenty of impurities. If I have plenty of impurities, we can use central limit theorem to say that all this impurity will randomly add, and you know that then any kind of disorder goes back to a Gaussian type of disorder. Okay? So I can use central limit theorem.
Why is the weakness of the disorder important for the system?
Or because if you imagine that you have extremely strong impurities, you will distort the physics of the system really locally. And then the physics here is completely different from the physics there, and then till you reach the next impurity. So if you want, there is a characteristic length scale in the system which then becomes shorter than the distance between impurity, and then you cannot use central limit theorem. But if I assume that I have a correlation length inside the system, but which is very big compared to the distance to impurities, between impurities, then I can, each little blob of the system has to deal with 1 million impurity, and then I can replace these individual impurities with a Gaussian approximant problem. So that's the main reason. Yeah?
I have two questions. In the beginning, when you talk about the disorder potential,
yeah.
So V naught is the same for all impurities.
Yeah, that's of course a simplification. You can imagine a more complicated type of disorder where V naught will be itself a function of the impurity, but actually it's not a crazy form in most solids. Because, for example, imagine you have some substitution inside the solid which acts as an impurity for the electron gas. Well, it will be the same everywhere. You have, I don't know, oxygen vacancies in a high TC superconductor. Well, every time you get the vacancies, it's roughly the same strength. And then it's mostly the position of the disorder which makes it random. Of course, again, you can imagine that now you have two types of vacancies, and this is perfectly possible to replace this by a V of Ri as well. But even if V0 is uniform, the fact that the positions are random will give you a real genuine disorder. Yeah.
And the other one is the double averaging.
Yeah.
I think the averaging order matters.
Oh yes. Oh yes, the averaging order matters. And you will see why a little bit later. I'll come back to that. So the averaging has to be done that way. I have one realization of the disorder. I solve my quantum problem, however, whatever it is. Then I repeat the experiment with a different realization of the disorder. I solve my quantum problem, and then I continue, and I continue, and I continue, and then I average all these results over the probability of finding one realization of the disorder. Now, you could tell me, but look, experimentalists don't do that. Experimentalists, they have one sample, they measure one sample, one realization of the disorder. But the sample is supposed to be so big, 10 to the 23 atoms, that different regions of the sample will correspond to different realizations of the disorder. So you make a very strong assumption, in that case, is that the system is called self-averaging. And of course, there are cases where it will be completely wrong. And you will hear in the course of Gil Raphael of the case of strong disorder, where here you have to make take very good care of studying the full probability distribution of the disorder, because this question of what is the average and what is the typical realization and what is the median realization and so on becomes especially important. Here, in this lecture, I will focus mostly on the opposite case, so you will have the two limits which will be taught in this school, where you assume that the disorder is reasonably weak, self-averaging is supposed to take place, and we can sort of not worry. And then it's of course much more convenient for theorists, rather than say I have a single realization but with 10 to the 23 atoms, to do this statistical average over the disorder, rather than say I have to take a very complicated thermodynamic limit here, making sure that this realization is self-averaging. So this is a theoretical convenience, not a realistic. Yeah.
So you said if the disorder is weak enough, or but when you say disorder is weak enough, you mean that the impurities are dense enough?
Yeah. So you can. It's a very good question. I will come back to that. So I mean that either V0 is weak enough, or N is large enough.
So and then you said that means that it approaches a Gaussian distribution. But what is Gaussian distribution?
Now let me come back to that. Yes. There was another question here, but okay.
So even if disorder is weak on average, it could have some distribution, and there could be rare region effects.
Oh yes, and there will. Yes.
Is there a way to know before doing the calculation whether we have to worry?
You want an honest answer? No. No. So, I mean, of course, there are ways to know before doing the calculations, but you will see that even with a Gaussian distribution, there will be rare region effects. If any, Gaussian makes it worse, because Gaussians are very large tails, which will realize very improbable distributions. So one has to be, the message is that one has also to be extremely cautious when using this Gaussian distribution for the disorder, because it introduces some artifacts which do not exist with realistic distributions of disorder. And we'll see some of these artifacts, but usually this one you can spot relatively easy. But the fact that there are rare events, the fact that there are rare regions, we'll come back to that, and that's always there. Whether they matter or don't matter, that's another question. Depends very often at which energy you're probing the system, but definitely rare events will not get away without them. Are there other questions? Yes?
Maybe one question to clarify. So when you say that the disorder is weak, you want to also basically ignore the classic Anderson localization, right?
No, no, no. It's just a statement on the disorder. I'm not ignoring anything. For the moment, I have not even told you which system I'm looking at.
But the classic model of Anderson localization is assuming that the hopping is actually an order of whether the hopping energy is...
No, in 1D, any weak hopping randomness will produce Anderson localization. So, of course, in high dimension, it's not the case. But again, maybe let me make explicitly this mapping to the Gaussian disorder, or maybe not completely explicitly. And then if you still have questions on this question of weak disorder, we'll come back to this point. There was a question by you.
I mean, just to be clear, if it's really the variance that determines how strong it is. I mean,
yes.
If all the impurities are uniformly distributed, let's say, and they're all the same strength, then you go to disorder-free limit. No, because their position is random. Right, but okay.
No, that's as disordered as anything you might.
Mean the average property of that potential is not important. How strong that average potential is.
Oh yeah, but the fluctuations, if you want, this potential here fluctuates between V0 and 0. And the point is that it has extremely strong fluctuations locally. But now if okay, so maybe I'll go to this mapping because I guess I tried to put the cart before the horse. So let me explain what I mean. Let's imagine that I can consider that my fermion or classical or whatever, and maybe the best way to view that is to consider a classical object. It's very simple and visualizable with a classical object. Imagine I have a line, here a polymer, which can be characterized by a displacement u compared to a vertical position, compared to a flat position. And now the question I want to ask, I put a bunch of impurities here, and I want my line to balance its elastic energy, which will be the gradient square of the displacement, something which would like the line to be flat, if possible, with some elastic constant, and the fact that this line likes to go through the impurities, so that if left by itself, it would be very happy to do something like this. Okay, no, not go back, but this part is not very good, but we could do something like this, for example. Okay. So now, what will happen? If I have extremely strong V0, then it's pretty clear that the red line is what will happen. Because if V0 is extremely large, then the line will ignore this elastic energy and will simply go through every single one impurity that it can. Okay? That's the limit of what I call strong disorder. But now imagine that V0 is weak. If the line was trying to do that, it would distort a lot. So it would pay a lot of elastic energy. So in fact, it's much smarter for the line to do the following thing, which is to say, okay, I will try to find a characteristic length where the line is roughly flat, and then it sort of moves to another position and then another position. So the stuff is roughly flat, but then it tries to optimize within this thing what is the best position to be compared to the impurity. Which means that there is a characteristic length scale here, let me call it psi, and that the potential that the line will see will be the sum of all the potentials of the impurities. And then, indeed, by central limit theorem, you know that you have an average plus a Gaussian fluctuation. So you can view the potential here in this region as some average, which I don't care, plus something which I call delta V of z, of x and z here, which will have Gaussian fluctuation. So in other words, what I'm saying is that if my characteristics property of the system vary on some large length scale, then this region is practically homogeneous and is sensitive to tons of impurities. And what I can do then is to replace this ton of impurities by something which will be this delta V of R. And this one will be Gaussian. And essentially, the strength of these Gaussian fluctuations is Ni V0. Okay? So what I did, I replaced the problem with two, characterized by two numbers, V0 and Ni, by a problem which is characterized by a single number, which is the fact that now I have a Gaussian potential, which, if I average over the disorder, will have a single number, let me call it D, and let's say delta functions correlations, but that's not mandatory. I could have longer range, F minus R minus R prime correlations. But the point which is important is that now this object has Gaussian correlation, which means if I try to compute higher moment of the potential, they decouple into products of the two moments. And that's a great simplification because it means that essentially now if I have higher correlators, I can always reduce them to 2-point disorder correlator. By the way, this is exactly what Anton did in his lecture, where when he did the average over impurities, they were always averaged 2 by 2. which strictly speaking is not correct. If it was a very complicated impurity potential, you could imagine 4-point correlators, 6-point correlators, and so on. The assumption that you relate only one impurity with one impurity is the idea that the correlator, the fluctuations of the impurity, is Gaussian. Okay? So if I have something like this, I can also do it in Q space. So I can say that the correlator delta V of Q, delta V of Q prime is delta of Q, Q prime times my function FQ, which is traducing here the real space correlator of my impurities. Of course, if I have delta function correlations here, this FQ is a constant, simply. So if this is a constant, then it means that I have delta function correlations for the disorder. Okay, if I want to write the probability distribution of delta V, this is simply exponential of minus sum over dq f minus 1 of q delta vq star delta vq. So you have a Gaussian probability distribution for the fluctuations of the disorder. Okay? And that's essentially, except explicitly stated, what I will consider as my probability distribution for the disorder. Okay? And again, I'm not doing anything different from what you already saw in the previous lecture. Okay. Now, it means that I still have something complicated to do, and so I still have the average to do with this probability distribution. Okay? So I have various possibilities. The first one is to really compute the quantum problem for each realization of the disorder. As I said, this is something that in a way will be done in a, of course, much smarter way in the course of Gil-Raphael, where you will see this real space renormalization group technique, which carefully remembers all the probability distribution of the disorder. So that's one possibility, very adapted for strong disorder. Then the second possibility is to say, let me try to do the average from the start. Okay? So let's see what I have to do. So if I want to compute the average of an operator of a disorder, I have to do the average over all realization of delta V of exponential of minus, okay, let me write it delta V squared here. You understand what it means. This is this object. Okay, I have then 1 over blah blah delta V exponential of minus delta V squared to normalize the probabilities. And then I have the quantum average. And the quantum average I can write as path integral as sum over d phi. The operator is a function of phi. And then I get exponential of minus the action of the pure system plus integral over delta V times rho divided by the integral over delta phi of exponential of minus action of the pure system plus integral over delta V times rho. So this is the thing I have to do. Oh. And now I have problems.
I have one question.
Yeah.
Is the denominator still in the exponential, or is the denominator now?
No, so this is, okay. So this is a factor. And the exponential is only the probability for the disorder, and then it's multiplied by this ratio. Is it clear? So this is the integral dv, p of v, times the average of the operator on quantum fluctuations. It's clear? And this one is the denominator which normalizes the probability distribution, because my Gaussian here is not normalized. Okay? Now, then there are various ways I can proceed. The first one is to say, oh, but I just need this expanded in powers of delta V. Then I just do standard power law expansions, and I will get standard diagrammatic theories with a certain number of powers of delta V. Then I average over exponential of minus delta V squared each one of the diagrams. And that's what you saw before, that you will get something which is blah blah, some diagram which contains delta V square, and so on, some diagram which contains delta V to the 4. So here I'm expanding this, both numerator and denominator, in powers of delta V, and then I can do the average, and that corresponds, when I do the average, to connecting the lines here in a certain way by this Gaussian propagator. That's what you saw in the previous lecture. Yeah.
So do you need the time integral over rho?
Well, here, of course, this is an action, so everything here is space-time dependent. The disorder is time independent. Okay? So typically, this is a path integral in space and imaginary time, or space and real time if you want, but at t equals 0 for equilibrium properties. But let's consider that this object is a path integral, let's say, with fields which depend on space and the imaginary time, which normally one uses to do quantum averages. Okay? So is it clear for everybody, this part? Because I don't know how familiar you are with either path integrals or imaginary time. Okay, nobody yells, yes?
Question, so if you had impurity spins, so they wouldn't move, but then there's the spin could move, then you would have time dependence.
That's a good question. So again, it depends what you call impurity spins. If you imagine a dynamical spin, then it would have time dependence, but then that would not be the quench disorder that I'm describing. The time dependence will have to be optimized at the same time than the rest of the fluctuations of the system. So we go back to the electron phonon type of problem that I was discussing. Then your delta V here will have to be integrated both in the numerator here and in the denominator. What I consider here is a disorder which is purely static. So you could imagine doing it by spin impurity, but then the spins are frozen, they never move. They don't flip. Okay? And that's quench disorder. So what you are talking about are very complicated problems of annealed disorder, where you put the impurities at random positions, but in addition, their essentially dynamics has to be taken into account. So that's an even more complicated level, because you have both the spin dynamics of the impurity and the randomness in the position of the impurity. So, but the spin dynamics would have to be treated at the level of the quantum average. So there would be here an integral on the dynamics of the spin impurity, and the only thing that would be outside here would be the positions of the impurity. So I would have then to do the average over the quenched position of the impurities. Okay, so there it falls still in the same category, but there my impurities would be part, let's say some degrees of freedom of my impurity would be part of this field phi, which is fluctuating with time. Okay. Are there other questions on that? Okay. So that's the standard diagrammatic expansion of disordered problems, and then there is absolutely no sort of conceptual difficulty. You can do order by order in each one of the diagrams. You can do the average, because now your delta V is connected by the propagator, which corresponds to this Gaussian integral. Okay. Now there is a better way to do that, or I don't know if it's a better way, but some people got more ambitious and said, but why can't we just do the average from the start? And indeed, it's very tempting, and that's where the Gaussian disorder is especially handy. Imagine there is not this denominator here. You get delta V squared here, and your perturbation is linear in delta V. So you want to complete the square. So you would be very happy to complete the square and just say, at the end of the day, I get exponential of minus rho squared. So I can do the average from the start. The thing which prevents you from doing that is the presence of this denominator. And that's what makes quench disorder problem difficult, is that it's not this you have to average, but it's the thing normalized by the denominator, and now of course you cannot simply complete the square. So people invented two methods to get rid of the denominator. And there are two very beautiful methods. One I will not talk about because I think Anton will do it. It's called supersymmetry. So, how to get rid of the denominator? Sorry?
Isn't there a free method?
Well, there is a third one which I will not which I will mention, so which is Keldysh. But this one I will not even write. Okay, so let's say there are indeed, as Leo properly corrects me, there are three methods. So the first one is supersymmetry. And let me just give you a glimpse of it. I will not go into detail. This denominator here is the denominator of a theory, which is a theory, and you saw it in Anton's lecture, which is something quadratic. If you have non-interacting particles. If you have non-interacting particles. So supersymmetry is for non-interacting. So the idea is that if you have a Gaussian integral, sum over dx exponential of minus a at x squared, you know that this is 1 over square root of it. And if you have a more complicated stuff, that's interesting. And if you have more, so let me put a squared so that I don't have, it's 1 over it. And if you have more complicated stuff, it's 1 over determinant of it. Okay? But this is because x are normal numbers. They are commuting variables. But if instead I use something called Grassmann variables, which are anti-commuting numbers, so that eta 1, eta 2 is minus eta 2, eta 1, then if you do the same integral, sum over d eta 1, d eta 2, blah, 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 so this then becomes 1 over determinant of the matrix A, of exponential of minus a eta, eta dagger eta. Instead of having 1 over the determinant, you get the determinant itself. Okay, so this is determinant. So the idea is to replace this denominator, which is 1 over a determinant, by a numerator, but on Grassmann variables. So instead of having blah blah, a numerator times 1 over blah blah, you just have the first blah blah, which is with commuting variables, and then you replace it by an integral over the Grassmann. You replace the second one by an integral over Grassmann variable. Which means now you just have a product, and then you only get exponentials in the numerator, and you can complete the square, and you're happy. The price you have to pay is that now instead of one field, you get two fields, one which is anti-commuting, one which is commuting, and that's why it's called supersymmetry. It's because you have a mixture of bosons and fermions. Okay? It only works for non-interacting particles. The second method...
Can I
sorry, yeah.
So non-interacting, does it also include interacting in the sense that after bosonization we have a quadratic Hamiltonian?
No, because you will see why a little bit later. The term of coupling to the disorder is not quadratic anymore once you have bosonized. So the whole Hamiltonian has to be quadratic, not only the kinetic energy. That would have been fantastic. During my PhD, I spent a couple of months trying to see if I could make this stupid method work for 1D interacting system, and at least I failed. The reason is that the coupling to disorder will be through a cosine term, cosine phi. And then there is no expression, at least no simple expression I know, which allows you to invert the result, because the stuff is not just a determinant, it's a more complicated expression. But you're right, you might imagine that in other cases, you reduce the system to something quadratic, and then you're free. In a way, you can do it with interacting fermions if you say they are in a Fermi liquid state, because then they are Lac free fermions, and then you're okay. But as soon as you have to deal with quartic terms or more, you're dead with the supersymmetry. Yes?
This supersymmetric argument at all similar to a Hubbard-Stratanovich transformation?
Not exactly. It's Hubbard-Stratanovich is a decoupling. So if you do Hubbard-Stratanovich, you would start from 4 fermions and replace it by an integral with an extra field and then only 2 fermions. Here it's really saying that something which is in a denominator can be written as an integral of something which is in a numerator, but you have to change the statistics. So I think for me it's a little bit different, but again, maybe it's a question of how you view it. By the way, you could imagine decoupling the interaction term with a Hubbard-Stratanovich transformation and then use supersymmetry, but the integral over the extra field are not put in the right place and it doesn't work either. So it's really for non-interacting fields.
Excuse me?
No.
What's the potential dependence or disorder dependence?
So it's the same. It's exactly the same integral.
Exponential.
Yeah, it's exactly the same integral you had with commuting variables. You replace it with anti-commuting terms. But let me not go too deep in the supersymmetry because Anton told me he would do it. So the second method, which I will not talk at all because it would be a whole lecture in itself, is called the Keldysh Technique. And it's a way to write time-dependent, so it's much more it's a way to write time-dependent quantum problems. It's very powerful, and it has no denominator. So if I use the Keldysh technique, I will get the same average, but no denominator. But the price I have to pay is that I have a much more complicated action. Okay? And believe me, if you have an equilibrium problem, so something which is not explicitly time-dependent, it's very rare that you can gain on the standard Matsubara technique by going to Keldysh. You will hear about Keldysh. I get Alex now will give a course on Keldysh. So I will not talk about it, but it's a great technique. And indeed, you can get rid of the disorder from the start in this technique. So let me just mention briefly the last one, which is called the replica method. And this one works for equilibrium problems, of course. It works independently on what is the problem. And you will see what is its little drawback. Okay, so what is the idea in the replica method? Well, the idea is that I have this object here. So I have this thing, and I have a denominator. And then someone smart noticed that the power -1, the smart guy was someone named Sam Edward, who is someone who worked on essentially spin glasses. And essentially, the idea is to say, okay, I have 1 over the integral over d phi exponential of minus s blah blah of v, which is what I wrote before. And I will write that as the integral on the numerator of d phi exponential of minus s of v to the power n minus 1. And if I take n equals 0, then it's the same thing. Great idea. Which means that my numerator d phi O of phi exponential of minus s of v divided by the denominator d phi exponential of minus s of v can be rewritten as sum over d phi O of phi exponential of minus s of v. And then power n minus 1 means I just copy n minus 1 time the integral d phi exponential of minus s of v, blah blah, n minus 1 times. But then I have n fields, and what I have is the integral over d phi 1, d phi 2, d phi 3, d phi n of the operator, which is only a function of the first field, phi 1, and then I get exponential of minus sum from I equals 0 to n of s of the field phi I and v. So I've now replaced my complicated fraction by something which has no denominator, but with the price of having n fields. And now I can do the average. Okay? So let me do explicitly the average for you. So for example, if I say that my action is S0 of the field phi plus sum over dx of v of x rho of x. So rho is a function of the density of field phi. It doesn't matter what it is. What do I have? I have to do the integral over dv exponential of minus v squared. Then I get this sum over d phi 1 d phi n O of phi 1 exponential of minus sum from I equal 1 to n of S0 of phi I minus the sum from I equal 1 to n of v times rho of phi I. I remove the integral, you know that they are there. But now it's very simple because I have this and I have the square, so let me complete the square. And what I get, the integral over dv goes away, is the sum over d phi 1 d phi n of exponential of minus sum from I equal 1 to n S0 of phi I exponential of minus the square of sum from n equal 1 I equal 1 to n of rho of phi I squared times d, where d is the amplitude of the disorder. So I have replaced a disordered problem by a problem of n fields. Each one has the same action. The actions just add for the pure case, but the disorder generates an interaction between this n field. Okay? So what I have traded is a random problem for a problem of n interacting fields, and the interaction is mediated by the disorder. If you want, it's the child of the disorder that I had before in the problem. And we are emotionally well equipped to deal with interacting fields. There is a lot of approximation methods and blah, 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 which have been made to, and this is exactly the object I wanted to compute. This is the quantum average of O of phi averaged over the disorder. So the operator, sorry, you should have shouted that I have forgotten the most important part, which is the operator, which is only a function of one of the fields. Okay, so it's O of phi 1, could be any one of them, phi 2 or phi 3 or phi 4, it doesn't matter, but one of them, and it has to be averaged with this. By the way, you can put the denominator, if you're not happy that I removed here the denominator, you can put it back, not that way, but you can put it back, because you notice that if I put here sum over d phi 1 d phi n of exponential of minus sum over I equal 1 to n blah blah, this object will be proportional to 0 in the limit n going to 0. But let me ignore the denominator for the moment, it doesn't matter. So you have traded a random disorder for an interacting field problem, but there is a catch. The catch is that you have to solve the problem for all n, and then do an analytic continuation, and take the limit n goes to 0. And when you do that, black magic happens. And trust me, it's really black. And we'll talk about it a little bit later. So this is a very generic method. I mean, it works for classical problems. It has been used extensively for spin glasses. It has been used extensively for studying disordered elastic systems. It has been used extensively in quantum problems. So this is a very generic method, but it doesn't solve the problem for you. It just replaces the disordered problem by a non-disordered problem. So you have full invariance by translation, you recover all the symmetries of the original problem, and so on and so forth. So it sounds very good, but again, the price is that now you have n interacting fields. These n fields interact via a term which is the consequence of the presence of the disorder in the original problem. By the way, they can also, each field can also interact with itself in the action S0 can be an interacting object. But they are not coupled, the replicas are decoupled, and the disorder term is what couples the replicas.
This interaction, could you treat this with bosonization? It looks like you could. Just
this one? Yes, of course. Yeah, of course. That's the idea. But you can also treat the other interactions here by bosonization. So this is a method that goes well with bosonization because it doesn't care about whether I have linear or non-linear or whatever term. I didn't practically specify. Here I say rho, but rho could be anything. It can be any operator. The only thing I need for this method to work is a Gaussian disorder and a linear coupling to the disorder. So you need here in the action that there is something, doesn't matter what this operator is, but it needs to be linearly coupled to the disorder because otherwise you cannot complete the square in the exponential. Okay? Yeah?
So can you explain what guarantees that you get a meaningful result when you take R goes to 0?
N goes to 0?
Yeah.
Well, let me say it that way. You get no guarantee at all.
Okay.
And as usual in physics, you have to do it. And then you see whether the results you get is crazy or not crazy. So I can tell you what happened for spin glasses. Some people solved the problem of spin glasses with this method. And then they started to find negative entropy, very weird results. And then the whole community realized that you had to do something special with these replicas and that the limit n going to 0 was highly non-trivial. And the person who cracked the problem of this limit is someone named Giorgio Parisi, who invented something called replica symmetry breaking. And I'll mention that, but tomorrow, not today. So indeed, when you take the limit n goes to 0, a lot of bad things can happen. But in most of the cases, it works. And even when it failed miserably, people found a way to plug the hole and to find a meaningful way to take the limit n goes to 0, which gives pretty damn good physical answers. So it's not guaranteed. It suffers from all type of analytical continuation problems. You could ask the same thing. How can I be sure that when I take I omega n in Matsubara space goes to omega plus I delta, I recover the retarded correlation functions? Well, you're not guaranteed in general cases, but in most cases it works very well. And it's the same thing here. So you really have to solve the problem for all n, take the limit n goes to 0, check whether there is this horrible phenomenon of replica symmetry breaking which takes place. And if yes, there are ways now to deal with it. Before Giorgio Parisi, there was none. So that's why people found negative entropies. And then you will see that you can extract very meaningful answers out of this method. Yeah, Leo?
But also, I mean, that's why maybe it's important to have these two other methods.
Yes. Yeah, so except, as I said, supersymmetry is not applicable for interacting problems. So the only one is Keldysh. And so far, solving interacting bosons in 1D with Keldysh, to the best of my knowledge, has never been done. Because it's, I mean, you really have to sweat.
Interacting bosons?
Interacting bosons. Yes, even with bosonization. So doing this thing we did with replicas is pretty tough with Keldysh. Yeah.
So you can't generalize the Zalezhinsky-Larkin fermion calculation to Keldysh?
The Zalezhinsky-Larkin calculation is fantastic, but it's only for pure fermions with only forward scattering interactions. So as soon as you go beyond that, this calculation doesn't go through, but then bosonization takes over. So if you want bosonization, it's a generalization of the Zalezhinsky-Larkin. But the difficulty now, as we will see in the half hour which remains, is to add the disorder term. And you will see the disorder term is relatively ugly. One thing that I would say has not been really done, in fact it has been partly done, I will discuss about this, is to do the opposite, is to solve first the disordered fermion problem. For bosons it doesn't work simply, I will explain why, but for fermion it works. You solve the disordered boson problem, fermion problem, so Anderson localization, and you try to reintroduce perturbatively the interactions. And to some extent, Sasha Mirlin carried out this program, and also Alainer, Basco, and Altschuler, and this is what sort of led to these issues of many-body localization. Again, let me emphasize that here we are implicitly dealing with many-body localization. We are talking about the many-body problem, so interacting particles, and we are studying the effect of disorder on it. So we are not doing Anderson localization of single particles. Okay. Yeah.
So is it like that you have some problem taking n going to zero limit, like the fact that you're introducing extra symmetries in the action by?
Yes. So well, first you see that the fact that -1 is equal to n minus 1, n then is replaced by an integer because I add a field. So you have to do an analytic continuation from 1, 2, 3, 4, 5, 6, 7, and that to 0, which in itself, in mathematical, in pure mathematical glory, has its own set of convergence radius and things like this. But in part, you're absolutely right. There is a symmetry which has been added here, which is the symmetry of permutations of the replicas. Because I can take any order for the replica I want, I can replace this phi1 by any order, and you implicitly assume, when you take the limit n to 0, you have to make an assumption on how this symmetry is carried out. The simplest assumption, which was the one that was done by the people who initially invented this method, is that the symmetry is unbroken, because there is no reason to break it. Okay? And then, as I said, in several cases it works, but in several cases it gives completely wrong result, and what happens is that you have to break the permutation symmetry of the replicas, and the beauty of it is that you can break it in a way which is consistent with taking the limit n goes to 0. I give you a little exercise which is very easy, you can do it for tomorrow. Imagine you have a matrix which has one value on the diagonal and another value away from the diagonal. So this is M. Okay? The matrix is n by n. I want m minus 1. And then you can show me that these formulas will carry through if you take the limit n goes to 0. So you can invert 0 by 0 matrix which have this structure. Do it. It's not complicated. Yeah.
Is there an interpretation to the replicas in terms of the disorder?
Physical interpretation of the replicas? That's a good question. Maybe there is, but I don't know it. No, what I mean is that there are people who manage to pull out, especially in the spin glass community, saying that you can introduce a distance between replicas and that it reflects the profile of metastable states in the system and whatever. For me, these are just words that I must say I don't really emotionally relate to. So I view it essentially as a mathematical trick. And I have a little bit the attitude, but I admit that's my personal attitude, and if you talk to other people like Marc Mézard or Giorgio Parisi, who are, of course, great specialists of this method, they might give you other, let's say, answers. But for me, I'm not trying to find a physical interpretation in the replicas, and the only thing which interests me is whether if I use them, I get the right answer, or I get nonsense. And it's a method that works.
Yeah, how do you know if it's correct or not?
If it's, sorry?
How do you know if I do replica trick, and how do I know, did I do something correct or did I do something wrong?
Oh, so far you did everything correct up to here. There's no problem.
I mean, if I take n goes to 1, that's 0.
Okay, so maybe this answer will become a little bit clearer as we move forward and as we use this type of technique. So let me maybe give you an answer. If you are dealing with a perturbative expansion of this guy, then it works 100% of the times, because then this is just a bookkeeping device to keep the structure of the diagrams correct. And everything you had done by this method, you could have done directly by expanding first and doing average order by order on the disorder. So if you do a perturbative expansion to a certain order, or partial resummation of classes of diagram, this is a 100 foolproof, and even if you don't know anything about replica symmetry breaking, this works. There is no replica symmetry breaking, and this is just something which will ensure that when you write a diagram like this, to take the notations that you already saw, where I put an impurity, and then I have another fermion line which is like this. A diagram like this, before you average of a disorder, is a disconnected diagram. So it should go away. Okay, it should disappear, it should not be counted. Now if I do the average, I would draw a line here. Okay, so it looks like a connected diagram. Now, how do replica help you get rid of this? This is the field phi 1. Okay? So this replica index here doesn't change. This can be any field phi j, and the sum goes from 1 to n. So this diagram will be multiplied by a factor of n. So when you take the limit n goes to 0, it dies. So the replicas ensure that this type of diagrams will be wiped out from the perturbation series. And there, it's a bookkeeping device, it works fully. The problem is more when you try to do approximation, like saddle point approximations or whatever, at the level of the action. Then, okay, then you have to see. And we'll see one, and maybe it will be clear in that situation. But perturbatively, even sort of infinite perturbation series, this is perfectly foolproof thing. Are there other questions? Yes?
Have you ever seen a situation where someone didn't take the limit all the way to n equals 0, or just kind of stopped part way?
Yeah, but then you don't recover the results for the disordered problem. So there are other use of this type of method. For example, the method, yesterday I was mentioning that you know, when you take this Tonks limit, you go from bosons to fermions, but you have to change the signs in the wave function, blah, 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 and it's complicated. There is a trick to do this with introducing replicas of the system. And there you have to end up, I forget, n equal 1/2 or something like this, and that works. But that's not the one for disordered system. If you want to recover the results for disordered system, you have to take the limit n goes to 0 of this expression. Otherwise, it doesn't reproduce the original average you wanted to do. So if you stop midway, you're solving another problem. You're not solving the disordered problem. Yes?
There's another example, a very physical example of self-avoiding polymers, where the contour is represented by a Feynman diagram.
Yes.
And if you want to exclude configurations where a polymer bends on itself, intersects itself, you take n goes to 0 limit.
The mapping of the Ising model with n component and taking the n equals 0 limit was part of Deugen's Nobel Prize for studying self-avoiding walks in polymers. So there are other replica techniques. Here I'm mentioning the one which corresponds in doing this type of disordered systems. Are there other questions?
So here, in that sense, the replica parameter n here is like plays a similar role like the n capital N in large N expansion, right? So we have no such diagrams.
Yeah, so if you want okay, first we take the thermodynamic limit. So the large n is sorry, not the size, yeah. So the size is taken to infinity, but the large n limit, yes, is a little bit a control parameter which allows you to solve and write a saddle point for the thing. Here, the replica parameter doesn't help you to get a simpler solution. It just sort of helps you to get rid of the disorder. So if any, taking this limit n goes to 0 is complicating your problem, not simplifying it. Usually when you take the large n limit, extending groups to SUN, for example, you do that because taking the n equal infinity limit is helping you getting a simple saddle point or whatever. Here, very often, you will find that solving this problem for n equal 1 or n equal 2 or n equal 3 is highly trivial. But you need to solve it for all n, and then the limit n goes to 0. I'll show an example tomorrow probably, where you immediately see what is the problem. That you will get saddle points which get inverted essentially. Yeah.
Is there anything specific for one dimension about it?
No. So all what I'm telling today is completely general. It applies to any dimension and it applies practically to any disordered problem. That's why I wanted to do it before we go deep in the boson in one dimension and whatever. I've not written what S0 is. It can be, you can solve the problem you saw in the first lecture technically by this method. It's not the right way, it's not the simplest way to do it, but you can potentially do it. Yes. Other questions? Okay, if not, then let's indeed move back to one dimension, which is now, let's move to one dimensional. 1D bosons plus disorder. Oh. So, what do we want to study? So we say we have a one-dimensional Hamiltonian of bosons that we already saw. So let me write it like this, H kinetic plus H interaction. So that's my pure 1D bosons. And then I want to add a disorder, and I will just add a disorder, which is sum over dx of my potential V of x times rho of x, where rho is the density of the bosons. Now, for fermions, we know very well that we can start from a non-interacting point and study the effect of disorder on the top of the non-interacting point. Can we do the same things for bosons? And the first thing I want to show you is that for bosons, U equals 0 is pathological. In other words, for bosons, you cannot sort of start by the non-interacting problem and then sort of say, let me add the disorder and study it a little bit like that. Why? Let me take even a simpler disorder. So I'll take a V of x.
U is the Hubbard U.
U is the Hubbard U, yeah. U means the interaction, the repulsion between the bosons. So let me take a very simple disorder, which can take two values, plus V0, minus V0, on each side. And I put on a lattice just for getting the argument as fast as possible. So I'll assume that I am on a lattice. It doesn't really matter. So I have a binary disorder, which can be plus V0, minus V0. Okay. Non-interacting bosons at 0 temperature, we all know what they want to do. They want to go all in the lowest energy state. So if I have non-interacting bosons pure, they are all in K equals 0 state. And that's it. They are all in a plane wave state with K equals 0, and the energy is 0, and that's it. I would not call that a Bose condensate, because it has no rigidity, but that's essentially all the bosons at the bottom here of the energy dispersion. Now, what will happen if I put the disorder? Yeah, sorry.
What do you mean by rigidity?
Well, I mean that normally if you want to test if something is a superfluid, what you do is that you twist the boundary conditions, or you put a flux in the system, and you see whether the energy of the ground state, how the energy of the ground state varies with this twist in boundary conditions. And if there is a sort of resistance to this twist, then it means you have a superfluid fraction. You have a superfluid stiffness, what people call superfluid stiffness. And non-interacting bosons don't have it. So that's why I don't like to call that a condensate or superfluid. But as soon as you will get repulsion, you get interaction, then there is such stiffness.
In 1D, right?
In 1D. Well, also in 2D or 3D, non-interacting bosons are not superfluid in 2D or 3D.
They do Bose condensate?
Well, again, there is a condensate fraction here, even in 1D, because everybody is in the K equals 0 state. So you get a macroscopic occupation of this state. But I wouldn't call this state a superfluid because it lacks this rigidity that you want in a superfluid.
It's a condensate, it's just not superfluid.
It's a condensate, but it's not superfluid. I think that's the proper way of saying it. Okay, now what will happen if I have disorder? If I have disorder, I will get a kind of thing like this. And now I have to find a place for my bosons. Okay, I have to find how they will do. So I will make a first claim. The first claim is that regardless of the size, I can always find a region where the potential will be minus V0 all the way. Do you agree with that? I have 1/2 probability of B plus V0 minus V0. So the probability of finding such a region is 1/2 to the power L. Okay, but it exists, it's finite. So if you give me L, I can tell you with a probability which is very small, which is 1/2 to the power L. So 1/2 to the power L, which is exponential of minus L log 2, so exponentially small probability with the size. This is a rare event. This is something which doesn't occur very often, but which occurs. Now, what will happen? I can try to put, it's a nice potential well, so I can try to put my bosons in this potential well. So let's see. If I put one boson, what is the energy of this boson? You see now that I have confined the wave function into a region of size L, which means I can consider, by uncertainty relation, that the momentum of the boson is of the order of h bar over L. Okay? Which means the kinetic energy is now, instead of being 0, is now 1 over 2m times h bar over L squared. Okay? So I lose kinetic energy. I confine my boson in one region of finite size. But I gain the potential energy, V0, which means the total energy is this, 1 over 2m h bar over L squared minus V0. Now, it's very easy to check that if I give myself a V0, there is always a size L above which I will gain energy. So if I have a rare event with L large enough, doesn't need to be infinite, just needs to be such that this is negative, okay, which means E total is negative, then I gain energy. So instead of putting the boson in k equals 0 state, I put it here. But if I can put one boson here, and they are non-interacting, I can put all the bosons. Okay? Which means that I have realized a system where I have here all my bosons, and when I say all, I mean 10 to the 23, in a finite region of space. Which means the density is infinite. Here, I have put a macroscopic number of bosons in a finite region of space. So it's a totally non-thermodynamic state, something which is absolutely not defined with a uniform density or whatever, and which is something that can only exist if the interaction is 0. Because as soon as I will turn on an infinitesimal interaction, because the density in this region is infinite, it will completely explode. Okay? So you immediately see by this rare event example that the limit of non-interacting boson is a limit which is non-thermodynamic, where all the bosons are confined within a rare event of the randomness, and which is a limit which will not survive any finite interaction. So the bosonic problem with finite interaction is radically different to the bosonic problem without interaction, which made this problem so difficult to solve because you needed from the start to put the interactions. For fermions, people got a lot of mileage by saying, let's look at the non-interacting problem plus disorder, and you already understand a lot of good things which survive more or less if the interaction is not too large. While here, you're dead. If you don't put interaction from the start, you're completely dead. Okay? Now, of course, then when I say that the thing will explode, it means that some of the bosons here will have to find other regions in space where they can be happy, which will decrease the interaction energy here, and then the system will evolve to something. Okay, so let's look on how we can solve the interacting boson problem. And if we solve the interacting boson problem, the good technique for that is bosonization. Why? Because it allows you from the start to sort of get rid of the interactions and focus completely on the disorder aspect. So if I have interacting bosons, then I know by this bosonization technique that I have an Hamiltonian, which is 1 over 2 pi, sum over dx, uk, let's say pi phi square, plus u over k, rad phi square. And I remind you that u and k depend on the interaction. So you see, that's a great simplification, because already my interacting problem is trivially solved. Now, the dictionary, yeah, just a second. The dictionary of bosonization allows me to rewrite the density in terms of the new variables. Yes, you had a question.
So my question is, the above argument also true for higher dimensions or just for?
So the above argument is true in any dimension.
Well, I mean, if you can, like, suppose we have a 2-dimensional or 3-dimensional system, and we can have all the bosons are still confined to the small region. But if we imagine there's a infinite length in this direction, I mean, even if you turn on the interaction, they can still repel in this.
Sure, but an infinite length in one direction with potential being minus V0 will be a rare event of probability 0. So you don't want that. You want a rare event, but which has still a finite probability. So you can get the potential negative in a circle, in an elongated space or whatever, but it has to be finite size. Otherwise, the weight of the exponential is killing you. So what I'm saying is that in higher dimension, you can repeat the same argument by saying I will have a region of space here where the potential is minus V0, and then you count the number of sides here, and it will be realized with a probability exponential of minus n, where n is the number of sides times a constant here. Okay? So, but if you try to make this region infinite in one direction, this is an event of probability 0. So even in higher dimension, you cannot move. But for non-interacting bosons, this is the only thing you need. As soon as you have a puddle where the kinetic energy can be lowered, they all fall there.
But things will be different if you have an external potential, right? Like a harmonic trap.
No, if you have a trap, then that's a different situation, because in any case, then the system is of finite size in a way, because the bosons cannot get too far from the center of the trap. But this rare event argument still persists. We will discuss it tomorrow. Yeah.
If I had long-range hopping or infinite dimensions, presumably I'd have to worry about tunneling from one rare event to the next rare event. Yeah. That might save me.
Yeah, so if you have non-interacting bosons, you don't have to worry about that. You find the best rare event, and then you put everybody there. So if you optimize the energetics of one boson, you have optimized the energetics of all the bosons.
But how do I know I have any localized states at the single particle level?
You mean that your stuff would like to jump on another rare event?
Yeah.
That's okay. You will just make something which will be a linear combination of the rare events.
Right, and I want to end rare events.
Exactly. But then what you would like to, or what you probably have in mind, is something where the stuff will percolate all over the place. If you have only one particle, you can check that this will not happen. It's relatively easy. I can always separate my objects sufficiently, and then this energetics will work. Where what you are saying is extremely relevant when I will get a weak repulsion, because then this is exactly what will happen. I will have one puddle, then the other part of the bosons will go to another puddle, and then another puddle to macroscopically occupy all the possible puddles. Because you have an infinite number of bosons, you need to occupy all the space. And then the question is indeed whether tunneling will take place between these puddles, and then I get back a superfluid, or whether there is kind of Coulomb blockade or charge blockade that will occur, in which case the things will stay on the puddles, and I will get a localized state. And we'll come back to that tomorrow. That's exactly the phase diagram of 1D bosons. That's the very question which is at the root of what is the phase diagram as a function of interaction and disorder for 1D bosons.
Could I rephrase the question slightly differently? So, I guess, am I guaranteed that, given a particular sort of non-interacting problem, single particle problem,
yes.
Am I guaranteed any localized states at all? Because if all my single particle states are delocalized, then I don't see how this argument goes through.
No, but you know that in 1D the single particle states are not delocalized. So indeed, what I am assuming here, and what you can show with this rare event argument, is that you can easily find one localized state for single particle, and then that's it. You just put everybody in this localized state. Yes, Theo?
Yes, I guess that's what I was going to mention as a high dimension. Let's say 3 dimension, you also need, for this rare region to matter, you also need some threshold beyond, right? To have a localized state.
You also need, I'm not sure, okay, that's a good question. I have the 1D argument let me think a little bit on that, because I'm not sure that you will not manage to pull out a rare event where you can get a localized state. Because I can make the tunneling as weak as I want by pushing the other wells. But okay, I admit that 3D I'm not so clear on that, but in 1D I'm pretty sure.
I guess a parameter.
So, I mean, the issue is whether the single particle state at the bottom of the spectrum
is localized or not. Yes.
And that may depend a little bit on the details of the disorder distribution, but certainly with lots of types of disorder distribution, you're exploring the Lipschitz tail, and it's certainly...
That's what I would have said, that you're deep in that.
You say goes through higher dimension.
Anton, you had the question? Yep.
Can it be understood as some order from disorder?
What do you mean order from disorder here? Order from disorder is usually the fact that you get a classical state which is disordered, but when you add fluctuations, let's say quantum fluctuations, paradoxically you would imagine it would disorder more, but there it would order the system.
Yeah, I mean the tunneling problem.
Yeah, here I don't know if I would like to view it as an order from disorder problem, because, but maybe you can tell me more what you have in mind, because I don't see the, here, of course, this is a quantum problem. If I had a classical particle, it would be even worse. It would fall down here in the bottom of the rare event, and it would not move at all.
I mean, in the question just now, there's different parts, and the tunneling between different parts, so that's the largest part we expect to localize.
Oh, I see what you mean. But then this is again something where you would have the need for repulsion between the bosons to occupy the other one. Yeah, let's talk about this tomorrow when we discuss the phase diagram, because this is still one of the big open questions on what is exactly taking place there. Are there other questions on that? Yes.
In this argument, we are looking just energetic.
Yeah.
Isn't the correct quantity free energy?
I'm at T equals 0 here. Okay. So I want to study the quantum phase transitions, the quantum phase diagram. So for the moment I set the temperature to 0, and we'll discuss how to put back the temperature. That's a big open question later. But for the moment, and unless otherwise specified, we are doing T equals 0 physics. So free energy is then equal to energy.
Yes. So you said you wanted to consider interacting bosons because non-interacting is uninteresting. If you have interaction strength that is less than V naught, the disorder potential, can you then say that it's basically non-interacting?
No, because you see that here I have a density which is infinite, which means that as soon as I will put 10 to the minus 20 interaction, this state is unstable. It has really to redistribute, and I can never put for interacting bosons an infinite number of bosons in a finite region of space. So they have to spread over the whole line and occupy states there. How they distribute is a complicated question that we will come to, but this state is really specific for non-interacting bosons.
But isn't it a question of order limits? Whether you take
well, of course, here I also, you're absolutely right, here I also implicitly assume that I have a macroscopic number of bosons, so I take first the n number of particles going to infinity limit, and of course, if now I have a finite number of bosons, then if my interaction is too weak, then this will be stable, because if n square, if you want, times the interaction is smaller than V0, then they will not want to move. But I assume that I have really 10 to the 23 bosons in my problem, and therefore any small interaction will make this system explode. Yes?
So So if I understand correctly, the main point is that so from this non-interacting bosonic problem, we cannot use anything about the problems, right? Yeah, more or less.
Sorry, I'm not sure I understood. We cannot use anything about.
So the argument is that say, the u equals 0 limit
is singular.
Is singular.
Is singular. Right. So you will not learn anything about the finite u problem by looking at the u equals 0 limit, contrarily to the fermionic case, where if you look at the non-interacting fermions, because fermions have this Pauli principle which prevents such events from occurring. If I was trying to do the same thing with fermions, I could not put them all here, even if they are non-interacting. Pauli principle prevents me from doing this, but for bosons there is no problem. So I'm just saying that the u equals 0 problem is one thing, and the finite u problem is another thing.
So what is the implications for applying supersymmetry in 1D then? Because you will then try to find out something about single particle localization.
No, you can do it for fermions, for example. You can apply supersymmetry for fermionic problems.
Right, but you will always have treat at once the bosonic problem and the fermionic problem, right?
Yeah, but there it's just a trick again to compute Gaussian integrals. So it has nothing to do with the statistics of the particle, of real particle in the problem. This trick is just to say I want to replace a denominator by a numerator. And in a way, it's a trick which is really at the level of even the Green's function. If I want to write a Green's function, I can write it as some integral of exponential of minus phi g minus 1 phi. Doesn't really matter whether initially I had bosons or fermions. Once I've reduced the problem to something like this, I just have a Gaussian integral to perform. And the supersymmetry is just to say, I want to get rid of the denominator, so let me put another Gaussian integral here over anti-commuting variable to do this trick. So the fact that we have disordered bosons, non-interacting, which are pathological, doesn't prevent you from using supersymmetry in 1D for treating fermionic problem, and it has been done very beautifully. There is a very beautiful set of paper by Kostya-Efetov where he does it, and it works very, very well. Okay, yeah, sorry, go ahead.
What happens when the interaction is irrelevant?
Well, the thing I'm showing you here is that it's very relevant. So it's when one should not get rid of the interaction. So that's, if you want for bosons, it never happens. So the interaction is always relevant. Okay, maybe let's finish on one thing, and just to let you think about it. What is this term? Sum over dx, v of x, rho of x giving in bosonization? Well, I use my dictionary. This will be rho 0 minus 1 over pi grad phi of x plus, and I'll just take the lowest order term, exponential of I 2 pi rho 0 x minus 2 phi of x plus the Hermitian conjugate here. So that's it. We have written the disordered term in terms of the variable phi and theta. And now we have to solve the problem of this Hamiltonian here, which is the interacting clean boson problem, plus this second term here, which is the random variable of the disorder here. Okay, this is a constant term, so it goes away. Coupled to either a gradient of phi and or coupled to this exponential. Sorry, there is a rho 0 here to keep it correct. Now you see that this is still a very nasty problem. This doesn't look too bad because it's still a linear problem, but this looks definitely nasty because we get cosine coupling, so a very nonlinear coupling to the variable phi, and we will see tomorrow how we can treat this thing, and you will see that there are interesting consequences that come to that. Okay, let's stop here. It's a good point to stop, and unless you have questions. No questions.